This video is on Aufbau diagrams. What's an Aufbau diagram? This is an Aufbau diagram. It looks pretty intimidating at first, but there are 3 rules that we're going to learn to follow, and then it makes filling one of these charts out really simple, and I think you're going to like it by the time we're done. So an Aufbau diagram is a way to write electron configurations. It's kind of like training wheels. I'm eventually going to take the training wheels away. As soon as you learn to love Aufbau diagrams, I'm going to make you do electron configurations without them. But let's learn how to do Aufbau diagrams first, and the basics of electron configurations. So electron configurations are the way electrons are arranged in various orbitals around the nuclei of atoms. Aufbau diagrams can help us to determine an element's electron configuration. And there are 3 rules to follow when filling out an Aufbau diagram. So the first one is called the Aufbau principle. It says that electrons enter the lowest energy level first. This can cause difficulties because there's an overlap of orbitals of different energies. This isn't difficult, however, with an Aufbau diagram. You just follow the diagram. You start at the bottom and work your way up to the top. The word Aufbau is actually a German word which means building up, and you'll be building up electrons from the bottom of the chart to the top of the chart. You can see the axis on the side that says increasing energy. It just shows you that as you go from the bottom to the top, you're getting more and more energy. So you just start at the bottom boxes and work your way up to the top boxes. The second rule is called the Pauli exclusion principle, and it says at most 2 electrons can fit per orbital. If the electrons are in the same orbital, they have to have different spins. Here's Pauli. He says no 2 electrons in an atom can have the same 4 quantum numbers. We're not going to get into what the 4 quantum numbers are, but if you have 2 electrons in an orbital, to show different direction of spin, a pair of electrons in the same orbital has to be written like this. So in your boxes on your Aufbau diagrams, you draw arrows which represent electrons. And if you have 2 in the same box, you have to show them with 1 arrow going up and 1 arrow going down. Rule number 3 is Hund's rule. It says that when electrons occupy orbitals of equal energy, they don't pair up until they have to. So if we were filling out a 2p sublevel here, and the 3 orbitals in it, and let's say we can fit 6 and we have 6, when you're filling out your Aufbau diagrams, according to the Hund's rule, you spread the electrons out first. They don't pair up till they have to. So up, 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 that's 3 electrons spreading out, kind of like sitting on a school bus. Nobody wants to sit together. The seats are kind of crowded, so everybody spreads out. But then as more people get on the bus, then you have to start pairing up. So then the next 3 electrons are drawn down, down, down. Okay, so let's draw the electron configuration for phosphorus. So the first thing we need to know is how many electrons does phosphorus have? That's what will tell us how many arrows we need to draw in the box. So if you go to your periodic table and you find phosphorus, you'll see that it has 15 electrons. So all 15 electrons need to be accounted for as arrows in these boxes according to our 3 rules. So 1 electron goes in the 1s. Can't move on to the 2s until the 1s is filled, so the second electron has to be drawn down in the 1s. 2 electrons per orbital. This orbital is filled, so we need to move on to the next orbital, which would be the 2s. So the next one goes up, and then the next one goes down. Okay, so that's 4 down, 11 more to go. So next there's the 2p. We go up, up, up. According to Hund's rule, they're going to spread out. They're not going to pair up till they have to, but I can't move on to the 3s until that 2p is filled. So I need to draw the next one going down, down, down. Okay, then I move on to the 3s. 1 arrow is going up, then the next one's going down, and then on to the 3p, up, 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 and I'm done. I have all 15 electrons in those boxes. According to our 3 rules of the Aufbau diagram, we started at the bottom and we built our way up to the top. We had 2 electrons per orbital. If they were in the same orbital, they're in different spins, 1 arrow up, 1 arrow down, and we spread them out before we paired them up, such as in the 3p. I didn't initially pair up the electrons here and here. I spread them all out. Okay, so now that I'm done with my arrows, this makes writing the electron configuration easy. So all we need to do is basically read from the bottom to the top with our arrows. So our first orbital, the 1s, has 2 electrons in it, 2 arrows, so I draw a little 2 above the s. Then I move on to the 2s, there's 2 electrons in that sublevel, in that orbital. Then the 2p, I have a total of 6 electrons, so I write 2p6. The 3s has 2 electrons in it, and then the 3p has 3 electrons in it. So this is the electron configuration for phosphorus. We'd read it like this: 1s2, 2s2, 2p6, 3s2, 3p3. Okay, let's try calcium. So calcium has 20 electrons. So we go up, down in sublevel 1s, and up, down. The 2p is going to have all 6, so we need to spread them out first. You always follow the rules, even though I know the 2p is going to be completely filled. So up, 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 and then down, down, down. The 3s is also filled. 1 up, 1 down. The 3p is filled, but I need to still spread them out again. Up, 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 down, down, down. The 4s is 1 up and then 1 down. Okay, so that's all 20 electrons. So we need to just read from the bottom to the top and say how many electrons are in which sublevels. So we write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So the orbitals fill in an order. They always go lowest energy to highest energy. And adding electrons can actually change the energy of the orbital. Full orbitals are the absolute best situation. That's the lowest energy, and that's what atoms like to be. However, a half-filled orbital has a lower energy level, and so therefore it's the next best situation. It makes the atom more stable, being half-filled than not filled. And unfortunately, this can change the filling order, which makes an exception to those 3 rules that you just saw here. So let me show you those. So if we were to write the electron configuration for titanium, which has 22 electrons, it would look like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So that's titanium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. If I asked you to do vanadium, all you would have to do is add in 1 more electron to get 23 electrons. Vanadium is the next one down the line. So vanadium would be 3d3, and you would just add a little electron in that third 3d orbital. If I asked you to do chromium, which has 24 electrons, you might think, okay, well, chromium is going to have 4 electrons in the 3d sublevel, so I'll just add an extra arrow in that 3d, like that. Unfortunately, that is not true. This would be the wrong electron configuration for chromium, for what I just said. A half-filled orbital or a half-filled sublevel is more stable than a not-filled one. So in situations like this, in the d sublevels only, you can take an electron from the s and give it to the d. So we would have 4s1, 3d5. There's that s electron leaving and going into the 3d. Okay, look at what I have now. The 4s is half-filled. It can fit 2, but it only has 1. Half-filled is not as good as filled. It was filled before, but it's still stable. And the 3d, by taking this electron, the 3d is now filled. The 3d can fit a total of 10, and it's holding 5. That's more stable than it's only holding 4. So this is what would happen with chromium and actually everything underneath chromium on the transition metals. Okay, here's another exception. Let's do copper. So if you followed the off-ball rules that I just taught you, you would probably get this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d would be 9, and we would have all of copper's electrons. but this is not the most stable arrangement. Let's look at what we have here. The 4s is filled, that's good. The 3d is not though, but we had one of those situations again where we can take an electron from the 4s and give it to the 3d. That leaves us with a half-filled s, remember s can hold 2 and it's now holding 1, and a completely filled d sublevel. So copper's configuration actually is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d10. So this picture here is showing us the irregular configurations of chromium and copper. Anytime you can take a 4s electron to make a d sublevel half filled, they'll do it because it's more stable in that arrangement. And also anytime you can take a s electron to completely fill a d sublevel, such as copper, that will also happen. So remember these exceptions. Anytime you see a D4 or a D9, it will never happen. It will always be S1D5 and S1D10. So Aufbau diagrams are an easy way to determine electron configurations. Like I said, they're training wheels. We're going to work with them in class and practice them, but eventually I'm going to expect you to be able to do electron configurations without them, and I'll show you how in class. You can draw arrows in the diagram which represent electrons that the element has following the 3 rules that we learned. Remember the exceptions of D4 and D9. Always be on the lookout for these. They will pop up on quizzes and tests to make sure you are really paying attention to these configurations and understand the rules. And an electron from an s sublevel in these situations is always moved into the D to either fill or half fill the sublevel because it's more stable that way. Like I said, this is pretty complicated. We will practice this more in class, but if you have any questions, please write them down and let me know.